In the farthest north, we have the Arctic, a frozen sea surrounded by land. But if we travel south, we encounter a frozen continent surrounded by sea, Antarctica. Its ice sheet is the largest mass of ice on Earth, covering over 14 million kilometers squared. In the eastern part of the region, the ice covers a landmass, while in the west, it actually extends to the seafloor, 2,500 meters below sea level. Contrary to what you might think, it's rare for it to snow in the Antarctic. That's because it's actually the largest desert in the world. Since the temperature is almost always below 0 degrees Celsius, freezing point, frost and snow crystals don't melt, only accumulate. Over time, it turns into ice. So, ice is just frozen water, right? Wrong. Well, right, but not entirely. Especially in Antarctica, ice comes and behaves in many different ways. So let's talk about 5 types of ice that many people can't distinguish: sea ice, iceberg, ice shelf, ice sheet, and ice stream. Unlike the others, sea ice is formed from salt water. It covers about 3 million kilometers squared in February to 20 million kilometers squared in October. The Antarctic essentially doubles in size in the winter. While only a few meters thick, sea ice insulates the ocean and prevents sunlight from penetrating the water. As a result, this slows the reproduction of phytoplankton. Heat also struggles to escape from the ocean to the atmosphere, keeping the air cold and dry. When the sea ice finally melts in the summer, it cools both the ocean and the atmosphere. Since ice is less dense than water, it floats. There are 2 different kinds of floating ice that are formed from fresh water: icebergs and ice shelves. An iceberg is a massive floating piece of ice that breaks away from a glacier or ice sheet and is carried out to sea. Ice shelves, meanwhile, are thick slabs of ice that form where a glacier or ice has approached the coastline. They don't experience friction and flow at about 3 kilometers per year. Some of these are actually larger than the entire British Isles. At the base of these ice shelves, seawater and ice come into contact. If it's warm enough, the seawater will melt the ice, which deposits cold fresh water into the ocean to make a water mass called the Antarctic bottom water, located at the deepest parts of the ocean. It is very cold and very dense, so as it spreads around the world, it helps direct the movement of the world's oceans. Ice sheets, on the other hand, are typically located over land. They're essentially a huge chunk of ice. The Antarctic ice sheet is the largest in the world, and it contains around 90% of the world's fresh water. The base of the ice sheet is typically warmer and it is more likely to melt. As a result, most of the ice and sediment discharged from the continent is through ice streams. When ice melts at the base, channels of water develop beneath the ice and lubricate it. They only take up about 10% of the volume of the ice, but ice streams can be up to 50 kilometers wide, 2,000 meters thick, and hundreds of kilometers long. In fact, they can flow at 1,000 meters per year. So what does ice matter to us? It still really is just frozen water. But it's not just frozen water. Ice cores are long cylinders of ice drilled from glaciers and ice sheets that help us to understand how the world and Antarctica's climate have changed over history. The ice cores with the longest, most thoroughly analyzed records are found in Antarctica and Greenland. As snow falls, it accumulates parts of the atmosphere along with it, allowing us to calculate the concentration of dust, ions, and CO2. Snow compresses into layers of ice, preserving these concentrations for millennia. Mixes of isotopes of oxygen and hydrogen, atoms of the same element with a different number of neutrons, tell us about past temperatures and how they have changed. Ice holds within it the data indicating changes in climate, local precipitation, temperature, wind strength, moisture, and atmospheric composition. Ice cores tell us more about climate change than anything else, and we can use them to place a context behind what humans have and haven't caused. The Vostok ice core in Antarctica was first drilled by the Soviets in the 1980s. It demonstrated to us that Earth's natural cooling and warming cycles have been significantly amplified because of recent changes in concentrations of CO2 and methane in the atmosphere. Come 1998, the Vostok project drilled into an ice core that was 11,886 feet deep. They were able to look back at 420,000 years of history, and it was confirmed that greenhouse gases indeed rise and fall with temperature. Despite showing that the warming and cooling of the Earth is a natural phenomenon, ice core findings also revealed that current levels of CO2 and methane are unprecedented in the amount of history covered by ice cores. Concentrations of greenhouse gases now exceed the highest points in the natural cycle recorded in ice cores for the last 800,000 years. The rates of increase have been unheard of for 22,000 years. Ice cores are essential to our research to determine whether or not we are at a high point of Earth's natural warming cycle, or greenhouse gases truly are being raised thanks to human activity. Scientists are worried that opportunities for this kind of research will suffer because of the increase in temperatures. Speaking of melting, some major ice shelves have collapsed in recent years. Satellites are also finding changes in the ice over the polar oceans. Meanwhile, the Arctic has reduced by 10% every 10 years. Glaciers in Antarctica and Greenland are 50% faster and will drain the ice sheets. By 2100, sea level could rise 7 meters. If all the world's ice were to melt, then it would rise about 70 meters. You might think that we can simply ignore this problem until it truly begins to affect us, but that isn't the case. We must work to protect the polar ice before it's irreversible. If emissions stopped completely today, it would take decades or even centuries to lower greenhouse gas levels through natural processes.